Okay, so I will start now. Hello everyone. So my name is Bach, and today I will present the landscape of formal verification in APL with a review and a case study in quantum computing. This is a joint work with Phuong and Santiago from National Center for Supercomputing Applications. So in this talk, we will provide two main contributions. The first one is that we will provide some preliminary work on formal verification of QAPL programs. QAPL is a quantum programming library written in APL, and also we want to show that quantum circuit expression and simulation benefits from languages where linear algebra is expressed naturally, like APL. Secondly, we want to present our approach when we are applying SMT solver to verify QAPL programs written in a subset of QAPL. This subset only contains defuncts only, with no external libraries. It also provides interpreters to translate APL to Z3, which is also a SMT solver. We also show some identification of invariants, pre and post conditions, and also some static verification prior to program execution. This is our workflow for this presentation today. So first we will present QAPL and how QAPL simulates quantum computation. Secondly, we will present the QAPL-V, which is the integrator of QAPL programs, and along with the verifier. And also we will show our perspective on correctness in quantum program. And lastly, we will present the future work on formal verification and APL. First, I will present about QAPL. So QAPL unknowns stand for Quantum APL. It's a quantum programming library written in APL. So basically, like we want to use APL because we want to explore quantum computing in both theoretical and practical side. We want to create a quantum software that people can implement at a high level. And secondly, we want to create programming languages that make quantum computer better and also prototyping the quantum computer architecture. QAPL abstracts like over the quantum circuit patterns with several motifs such as structural and parameterizable elements. And we also want to have some verification motifs that this motif will lead to verification of programs. This is an example of how QAPL simulates a quantum circuit for random number generation. On the left-hand side, you can see the quantum circuit, and on the right-hand side, you will see the QAPL code simulating the circuit. In this circuit, we will have a quantum state containing 4 qubits. These 4 qubits will go through the Hadamard gate and it will turn to the superposition state. All of these 4 superposition states will be going through the measurement states and will be in the destructive state, and then we will measure and we will have the output from that. The random element stands on the Hadamard gate and also the measurement one. Secondly, we will present QAPL-V and also our perspective of correctness in quantum programs. First, QAPL-V also stands for QAPL verified. It's an interpreter that will interpret the QAPL programs and also verify the QAPL programs also. In this graph below, it is our perspective, and it's our vision to put QAPL and QAPL-V into perspective. We want to have the QAPL and QAPL-V to maximize the productivity and the program correctness in quantum programming. The reason that we want to do verification is that we want to push verification towards security and correctness at the start of the quantum technology, and to avoid poor programming language in designing practices like a null pointer. Secondly, we want to have a correctness to address scarce quantum hardware, because right now we have a very limited quantity of publicly accessible quantum computers, and each time that we want to use any quantum computation is very expensive, about like $2,000 to $5,000 per hour. And also we want to deal with noisy intermediate scale quantum hardware, because right now this quantum hardware is very susceptible to noise sources like mechanical from mechanical or atomic decay. So there's some errors in quantum, like a bit flips. So the bit flip there is also in classical, but in the quantum the bit flip error is more common. So right now I will present some formal definition of QAPL program. So some formal definition of QAPL programs. So a QAPL program P is a collection of statements to encode and transform classical information using the laws of quantum mechanics. So QAPL statements have four types: the vector states, the qubits, the quantum gate operators, and the projective measurement operators. Note that the operator in quantum mechanics differs from the operators in APL. This is some sample of some primitives that implementing in QAPL. So as you can see here, the Q0 and Q1 representing the base states, which will represent in the column vector. The dagger one will be the function that returns the complex conjugate of the input. The input can be a vector or a matrix. The normalized one, because we want the normalized functions, because we want to ensure that every vector to be in the inner size. So we want to create a normalized state in order to after any operation, we can normalize the vectors down to have like a normal state. And also the QX, we will perform some kind of linear combination between these states. We also want to normalize it after, in order to have all of these qubit states to be in the unit size. Secondly, we have also simulate the block square, which represents the linear combinations between of any qubit state by the linear combinations of 0 and 1 in the base states of the qubit. And also we have some non-parametric gates like the X, Y, and Z gates also. And we also simulate some parametric gates where we rely on several inputs, such as like a X gate that we implemented over here. So this is some sample of some primitive that I have just represented to you. So next, we will have some correctness definition of QAPL program. So first, I want to define partial correctness in QAPL programs. So the first condition to achieve partial correctness is that all operators and functions in quantum mechanical parts in QAPL programs have to comply with the rules of quantum mechanics here. And secondly, condition to achieve partial correctness is that all of the pre and post conditions must be provably correct at both compile and runtime. So we want to extend the partial correctness to end-to-end correctness. I know that some of you will ask, like, why do we have two ways of correctness, partial and end-to-end? So basically, the reason is that right now, the quantum software relies on both classical and quantum size. So basically, like, we want to have partial correctness to be ensure that all the quantum program to be correctness on the classical side, and end-to-end correctness will ensure that it will be combining between classical and the quantum sides. So that being said, so QAPL, so we will define end-to-end correctness So a QAPL program, P is considered to be end-to-end correctness if P is partially correct that we have just defined. And also the outcome of P, and when it's running on the fault-tolerant quantum hardware, is the same as like the output of P when it's running on the quantum simulator on top of the classical hardware. And some fault tolerance properties that can be listed, that such as like a quantum computer has multiple physical qubits with a given fidelity, and a logical qubit is an error corrected collection of physical qubits as will be ideally specified. And we also have some safety and liveness for end-to-end correctness. So LNS to be the set of safety and liveness statement of the P, and we want to have all these sets must simultaneously for classical and quantum environment when P is executed at all times T. Next, we will have some example of verification of the Dues-Josa algorithms. So the reason that we choose the Dues-Josa, because the Dues-Josa is the algorithm that will perform in constant time in quantum computations, that will ensure that a function is balanced or constant. And this function is very significant, so we really want to try to verify these algorithms. So from this on the left-hand side is the Dues-Josa algorithm implemented in QAPL, and this part of code will go through the QAPLV interpreter, and this QAPLV will interpret into the Python code, and then it will going through the Z3 SMT solver, where it will verify our invariance, our requirements about invariance, assertion of pre and post condition, and also some safety and liveness conditions, and it will return some SMT code for verifying this function, for verifying this algorithm. And some of the APL subset for some QAPL interpreter right now that we have implemented, such as data, we have implemented like integer or real literals, and also we have some array operations. In terms of functions, we also have arithmetic operators and the defuncts. And in terms of operators, we have some combinators and the reductions, and so also others operators as well. And lastly, we will have some future work on formal verification and APL. So some future work, we would like to extend verification to a larger subset of APL. So we would like to have quantum algorithm library will bring new complexity, and we would like to reuse the interpreter for APL programs in general. Secondly, we want to integrate ZX calculus to extend the correctness guarantees, because ZX calculus encode abstract properties of circuits, and also ZX calculus will reduce the complexity of the quantum circuits. Thirdly, we want to study the role of the safety of APL interpreters, where because the robustness of the language moves the problem into the safety of the interpreter. And lastly, we will integrate the quantum noise models to the verification process in order to test how verification will go if we have the quantum noise model. And lastly, we have some summary and takeaways. First, quantum program verification is facilitated by APL. Secondly, QAPL provides a compact, self-contained platform to study the impacts of correctness and program safety in quantum computing. And lastly, fault tolerance is essential to define program correctness for quantum programs, which contain both classical and quantum elements. I think, yes, that's it. Thank you.
Thank you very much. Do we have any questions? Are we going to get your cameras on? Great.
Hello, thank you for the talk. I remember Santiago's talk from last year's APL conference, and I'm wondering, I sort of asked a similar question at that time about the size of the current systems you're able to currently simulate. I mean, it's known that classical systems get an exponential blow up for most classes of quantum systems. So how big of systems and gates are you actually working with and have tested with this?
Uh, mm. So right now we are at the beginning. So basically, we are trying to test some simple gates first. We are planning to have like a very enormous gates in the future. I think so.
I mean, what kind of sizes are you dealing with? Can you give just a few example numbers?
Sorry, can you speak that again?
What kind of, like, how many gates are you able to currently simulate on what kind of problems right now? Do you have some just examples that you might be able to say immediately?
So size. So let me just go back to this slide. So right now, we are trying to verify some of the X, Y, Z gate and also some X and Y gate on certain requirements that we have listed out. I know that there are some bigger gates that can be constructed, but right now we haven't tested or verifying on that.
Okay, thank you very much.
All right, thank you very much.